Optimization isn't just a foundational technique in environmental science and engineering. Optimization shows up everywhere. We study to maximize test scores, we search online for the lowest priced shoes. In video games, speedrunners attempt to minimize the time it takes to beat a video game, while min-maxers play to optimize character attributes. NASCAR racers optimize their driving. Stockbrokers optimize return on investments. In nature, animal traits and behaviors are optimized for long-term survival. Our minds and DNA are optimization algorithms, encoded as neurons and proteins. Optimization is so core to our existence that it's actually not hard to translate these ideas into computer language. Ecosystem models can simulate how trees compete with each other. This competition determines the composition of the forest floor, carbon sequestration, primary production to support animal life, and even the flow of water in streams. Forests are primarily driven by light and water. Feeding in a time series of meteorological conditions to an ecosystem model lets us simulate a time series of forest growth. The problem with these mechanistic models is that they rely on estimates of some biophysical properties that are very difficult to measure directly. Without good estimates of these parameters, we don't have good estimates of primary production. To solve this problem, we turn to optimization algorithms. Let's start with a time series of forest growth that we observed out in the woods. In the simplest case, we can try out different values for our model parameters and just visually compare how closely each model matches what we observed. This is okay, but our subjective interpretation of good can introduce problems. Which of these two models actually fits the data better? Two people might reach different conclusions. Subjectivity in science like this is not good, so instead we'll use an objective function, root mean square error. For each set of model parameter values, we have a time series of forest growth that we observed, and a time series of forest growth that was simulated by the model. If we calculate the difference between observed and simulated, we get a time series of what we call residuals, or how much the model missed by each time step. If we square the residuals, average the squared values, then take the square root of the average, that's the root mean square error. Root mean square error is just a measure of how wrong the model was on average. And with this information, we can objectively compare two model simulations and say which was better. Now comes optimization. We want to find the parameter values that give us the best possible RMSE score. What's your strategy when you play Battleship? Do you guess squares in order from left to right along each row and then move down to the next row? Probably not. You probably guess around the board at random. What you're doing is called Monte Carlo sampling. Think about each square as being defined by an x and y coordinate. By randomly picking squares, you might be uniformly randomly sampling x and y coordinates until you get a hit. Let's go back to our ecosystem model now. Suppose the model has two parameters, model conductance and routing depth, and these two parameters define the battleship board. And somewhere on this board is the best possible RMSE score that minimizes the distance between observed and simulated forest growth. One strategy is to just pick a bunch of random parameter values and keep trying over and over and over, and the best value that we found is our approximation of the global optima. This was a pretty basic algorithm, and we can probably do better. You might have noticed that the RMSE surface for this model was shaped like a bowl. Some parts of the RMSE surface only had really high values, so we didn't really need to spend resources to evaluate the model in those areas. Let's introduce a new algorithm. This one is going to pick a value and search randomly close to that location. If the randomly sampled parameter values are better than the previous best, we update to a new search location. This algorithm should move right into good RMSE values without wasting resources. There are many algorithms like the dynamically dimensioned search, Markov chain Monte Carlo, and genetic algorithms that follow this basic design. What happens if the RMSE surface isn't shaped like a bowl? What if there are actually local minima as well as a global minima for RMSE? There's a chance that this type of algorithm is going to get stuck in a local minima and can't find its way out. And in many cases, that's exactly what happens. One solution to this problem is to make the search neighborhood larger so that the algorithm can jump out of local minima. But this makes it harder for the algorithm to converge on a true globally best solution. Another popular solution is to run multiple search chains starting from different locations in the parameter space and then just pick the best one. This is more resource intensive. For these reasons, I actually prefer the simple battleship approach to model calibration and optimization. Optimization is as much an art as it is a science. Optimization is a critical step in our quest for objectivity in Earth systems modeling, and yet it is filled with subjective choices. Objective functions can weight residuals in subjective ways, often ignoring statistics. This problem led to a hilarious argument that lasted for years. Choice of algorithm, step length, number of chains, number of simulations, these are all subjective choices that you need to make. In the end, I think they're all the same. The best path forward is for you to use your own judgment and document your work. Have a nice day.